Good morning, guys. We are moving on with Unit 3. Today, we're going to talk about the p-value approach to hypothesis testing. Now, the p-value approach is very similar to the interval approach that we used yesterday when we did the critical value approach. Calculation is going to be very similar. The primary difference between these two tests, or the way that they're conducted, is in this approach we're looking at probabilities that a value falls in a certain area, as opposed to yesterday where we were comparing z-scores of two values. So again, you're going to notice a lot of similarities between what we're doing today and what we did yesterday. And I think that if you didn't struggle with yesterday's work, then today will be just as equally as simple. So you can see here we start out with the same example that we had yesterday. Jaron is just really adamant about being an excellent golfer, and that he can drive the golf ball 275 yards on average. So Misty just provided us with the table of data again. And I didn't get really creative because it's the same data from yesterday. So the sample mean's still the same. It's 264.4 yards. But Jaron is still insistent that he does drive the golf ball 275 yards. So at the 5% significance level, do the data provide sufficient evidence to conclude that Jaron's mean driving distance is less than 275 yards? So that would be Misty's claim. Before I go on, I do want to address one thing real quick from 3.1. So far I've just had one question about 3.1, and that just simply had to do with how did I want you all to write these out. So ignore everything for right now related to the problem at hand with this example. Let me just backtrack. With, say, question 1 on homework 3.1, I don't remember the exact number. We'll say it was 23 and a half days. It was talking about the lactation period for gray seals. So your null hypothesis, you would just simply write H naught is mu equals 26.5 days, maybe, I don't recall. And then your alternative hypothesis, on that one I believe it says differs. So whenever you see the word differs, it means that it is not equal to. Any other time it will be strictly less than or strictly greater than. But in this case we have differs, so it's 26.5. So that's your alternative hypothesis. And then it said to classify the test as two-tailed, left-tailed, or right-tailed. Whenever we use the not equal sign, it is a two-tailed test. Okay, that's all you have to do for, I believe, the first 5 questions on homework 3.1. Just write it out in the notation. Remember your units, okay? That is important. So I'm going to get back to the example at hand. Part A, state the null and alternative hypotheses. Well, with the null hypothesis, just like we were looking at from 3.1 there, in this case, Jaron's claim is the null hypothesis. He claims that his average driving distance is 275 yards. Misty is the one who holds the alternative hypothesis in this case, where she thinks that his average driving distance is less than 275 yards. So there's your null and alternative hypotheses. Now, the logic of this test is just simply that if the null hypothesis is true, then the mean distance of the sample of Jaron's drives should be approximately equal to 275. Now, yesterday we did talk about approximately equal. There will be a tolerance that we would be willing to accept. The mean could be 269 yards, and maybe that's within that tolerance. The mean could be 278 yards, and it might be within that tolerance. Approximately equal is kind of vague terminology, but mathematically, we can establish a certain range that we are willing to accept in order to determine whether or not we wish to accept the null hypothesis. Now, for part C, this is going to be exactly the same as what we did yesterday. Initially, it will be exactly the same. So for part C, we first established the sample mean is equal to the population mean based on our assumptions. So we're saying that mu is equal to 275 yards. Then we also want to look at the standard deviation of the sample. And the standard deviation of the sample is going to be represented by the population mean, or population standard deviation, divided by the square root of the sample size. I did not indicate it in the problem, but just like yesterday, we're going to assume that the population standard deviation is still 20 yards. So in our case, we're going to have 20 over 25. And we're going to get a sample standard deviation of 4 yards. And then we're going to set up the standardized version of x, or of x bar rather, just like we did yesterday by using the z-score. So remember, it's z is equal to x bar minus mu sub x bar over sigma sub x bar. And we know all these values with the exception of x bar. We're going to exclude that for right now because we're just setting up the equation. So that's going to be minus 275 over 4. So this represents our standardized version of x bar. And we can use that now to come up with any values that we need based off whatever x bar happens to be. And then that's where we're going to go to part D and apply this. So for part D, we have that mu sub x bar is 264.4 yards. So we can substitute that into the equation that we generated in part C. 264.4 minus 275. You'll notice there is no difference in what we did yesterday to today so far. And we get that's equal to negative 2.65. Now, here's where today kind of diverges from what we did yesterday. Once we've computed this standardized version of the sample mean, we ended up with the negative 2.65. What we want to do now is go back and look at the z table again. We're going to find negative 2.65 on the z table. Negative 2.65. So here's negative 2.6, negative 2.65. And we get an area of 0.00402. So we're going to use that value, that area under the curve, 0.00402. If I could operate my computer correctly this morning. You ought to not want to do algebra. So here we go. All right. So this is 0.00402. That's the area under the curve. What we want to do is compare that value to our significance level, the alpha value, which we note, that's off the screen, which we note right here is 5%. So alpha is equal to 0.05. So let's take our area and compare it to alpha. Make some notations here. If the area is the area less than or equal to alpha, is the area greater than or equal to alpha? In this case, we can definitely see that the p-value, the area, is certainly less than our alpha value. So when we end up with something like that, we reject the null hypothesis. When p is less than alpha, we reject the null hypothesis in favor of the alternative. We ended up rejecting it yesterday using the critical value approach. There was a little bit more calculations involved with it. We had to come up with the other z-score to compare it to for that critical value. Here we're not having to do the critical value. We're just simply looking at probabilities. And that's why we call it the p-value approach. Since our p-value is less than our alpha value, we reject the null hypothesis. With some of the terminology, really, here all you really need to know is the that the p-value here of a hypothesis test, this is I'm reading this in the green, is the probability of getting sample data at least as inconsistent with the null hypothesis as the sample data that was actually obtained. So we saw in the previous example that we were really, really, really close to zero. And one of the other rules you can also consider is the closer your p-value is to zero, the more likely it is that you will end up rejecting the null hypothesis. And that's indicated right here as well. The smaller or closer to zero the p-value, the stronger the evidence is against the null hypothesis in favor of the alternative. If the p-value is less than or equal to the specified significance level, we reject the null hypothesis. That's what we did in example 1. Otherwise, we do not reject the null hypothesis. So when your p-value, whatever that probability happens to be, is less than your significance level, you reject. If it is not, if it's greater than the significance level, then you do not reject the null hypothesis. So let's keep going. P-value of a hypothesis test equals the smallest significance level at which the null hypothesis can be rejected. That is the smallest significance level for which the observed sample data results in a rejection of H0, or our null hypothesis. I really got to learn how to type "the" in my computer. I type too fast, I guess. I always end up typing "te." So when we determine the p-value of a hypothesis test, we assume that the null hypothesis is true, and we compute the probability of observing a value of the test statistic as extreme or as more extreme than that observed. By extreme, we mean that it is far from what we would expect to observe if the null hypothesis test is true. Again, a lot of the terminology you'll get comfortable with as you see more examples. Determining the p-value for the one mean z test, we did this yesterday. We've been doing this several times over, so you are very familiar with this equation. The two-tailed test, it's no different than what we've looked at before. Left-tailed, right-tailed, same thing. So let's look at an example that maybe will help us out a little bit more with this example 2. We have that the value of the test statistic for a left-tailed one mean z test is z is equal to negative 1.19. So part A says determine the p-value. Well, because the test is left-tailed, the p-value is the probability of observing a value of z of negative 1.19 or less, because it's left-tailed, if the null hypothesis is true. That probability equals the area under the standard normal curve to the left of negative 1.19. So that's where we find our p-value. So we will look at the standard normal curve, and we're going to find what is the value at negative 1.19. Let me erase this, and we're looking at negative 1.1. Wow, I got way off there. 9. And we can see it's right here at 0.11702. So we'll go back to the notes here. P is equal to 0.11702. And that's our p-value. Anything less than 0.11702, we would reject. Anything greater than 0.11702, we would not reject the null hypothesis. And we now have, for part B, it says, at the 5% significance level, do the data provide sufficient evidence to reject the null hypothesis? So for part B, remember what we're looking at is P less than or equal to alpha. If so, then we reject the null hypothesis. Let me make a note here, if true. Reject. There we go. Okay, if it's false, then we do not reject. Well, when we look at our values, our p-value is 0.11702. Our significance level, alpha, is 0.05. So when we compare these two values, we see that our p-value is in fact greater than our significance level. So we do not reject the null hypothesis. If it happened to be less than, then we would reject the null hypothesis. All right, so example 3. We are kind of doing a very similar thing that we just did, except this time we're talking about a right-tailed one-mean test where z is 2.85. So here we want to determine the p-value. But now with a right-tailed test, this is our normal curve. Right-tailed test, we are observing the area to the right of the critical value, in this case z being 2.85. So what we have to do for this one in part A is it's going to be 1 minus whatever z 2.85 is. And so we're going to get 1 minus, and let's look to see what 2.85 ends up being. 2.8, 1, 2, 3, 4, 5 is 0.99781. So we will subtract that from 1. And we're going to get something that is approximately equal to 0.0022. And at the 1% significance level, so there's our alpha. Do the data provide sufficient evidence to reject the null hypothesis in favor of the alternative? So for this one, we are looking for a case where if p is less than alpha, we will reject the null hypothesis. And if p is greater than alpha, we will not reject the null hypothesis. So here our p-value is 0.0022. And we want to compare that to our alpha, which is 0.01. When we compare these two, we see that our p-value is in fact less than alpha, so we will reject the null hypothesis. Now, I know this is a right-tailed test, and you might think, well, shouldn't we check to see if it's greater than? We've done the subtraction, and we've altered the value for z, the z-score of 2.85. So we are, in fact, looking at everything to the left. And so this rule holds regardless of left-tailed or right-tailed test. So we will reject the null hypothesis given that our p-value is less than our value for alpha. And with example 4, we're going to see a two-tailed test. So here again, we have a z-score of negative 1.71. And what that means is we're looking at the area that lies to the right of 1.71, but also to the left of negative 1.71. So there is, don't get confused by this, but for part A, it's essentially going to be P, when we're doing a two-tailed test, it's going to be P times, or P is equal to 2 times whatever that value is for either one of those because of the symmetry. And then that's going to equal our p-value. I don't have to write that again. I've already written it. So let's look at negative 1.71 or positive 1.71. Let's look at negative 1.71. That's easiest because if we did positive 1.71, we would have to do the subtraction. So negative 1.71. We'll go back up to the negative table. Negative 1.71 is 0.04363. So we'll go back to our notes. And we're going to get 2 times 0.0463, which is going to be equal to 0.0872. So there's our p-value. Simply multiplying that negative side by 2 will generate both areas that we're looking at to eliminate. And then now we're going to look at part B, where we have a significance level. So when we look at our alpha, again, it's 0.0872 compared to 0.05. Well, we notice that 0.0872 is greater than the given significance level of 0.05. So here, again, we do not reject the null hypothesis. Okay, so the left tail test, you don't have to do any extra computations. The right tail test, remember to subtract from 1. The two tail test, you take the negative value and just multiply whatever that area is by 2, and then you can compare your significance levels. Okay, so the steps in the p-value approach to hypothesis testing is exactly what we just did. You'll first state the null and alternative hypotheses. Then step 2, you'll decide on the significance level if it's not already given to you. Step 3, compute the value of the test statistic. Remember that's your z equals mu sub x bar, it's x bar minus mu sub x bar over sigma sub x bar over radical n. Radical just sigma population. And then, so that generates your equation for the test statistic. And then you will determine your p-value by referring back to the z-table, finding that area under the curve. If p is less than or equal to alpha, you reject. Otherwise, you do not reject. And then you interpret that result. So here, just this chart kind of gives you a breakdown. If the p-value is greater than 0.1, then there's weak to no evidence that we should reject the null hypothesis. If it's between 0.05 and 0.1, then we have moderate evidence that we should reject the null hypothesis. If it is between 0.01 and 0.05, then we have strong evidence that we should probably reject the null hypothesis. And if our p-value is less than 0.01, then we have very strong evidence that we should reject the null hypothesis. And if you go back and look at the previous examples, you can kind of see where our given values of p fell into this chart and why we either rejected or did not reject the null hypothesis. And then so sometimes using that chart is handy because sometimes researchers don't explicitly refer to the significance levels. Previous examples, we had 5%, 1% alpha values. Sometimes we don't worry about that. We just obtain the p-value, and then you can refer back to the chart here at the top of the page and make a determination on whether or not to accept or reject the null hypothesis. That appears to be it. Yeah, okay. So there you will have your homework problems, and that's it. So I hope that you guys are having a great day, and I will be seeing you later on today. Everybody have a great morning,